Right. So surgery, you should know what is. And by surgery, in this case for fluids, I will refer to reconnections. Change of topology is the result of reconnections of surgery on structures, and I will focus on this type of reconnection. The so-called anti-parallel reconnection is, how to say, popular or scientifically justified 90% of the times. There are times where it is not quite clear what's going on, not in classical fluid structures, but at the quantum level, you may have what is known as tunneling. There are other very minor aspects that I won't cover. And right conservation is associated with the anti-parallel reconnection. I cannot go through a rigorous proof. I give you the idea. And of course, with anti-parallel reconnection, we have a helicity that has possibly to change, not always, but anyway. And this is another important thing. I'll mention connection between classical and quantum aspects, because what is amazing is that in quantum case, basically the mechanism is the same. And then I'll move to another context where reconnections or surgeries are playing an interesting role. It's not really about filaments, but it's about surfaces. So I'll mention minimal Seifert surfaces associated with fluid structures and evolution of plateau soap film. And then I show you something about the formation of a twist singularity when the topology of the surface changes for plateau films, soap films. As far as I know, this is the first time twist singularity evidence that something similar was described in the 70s under the name and then changed name catastrophe theory. So Al-Aziman or other people. So nowadays, of course, you could talk about singularity theory because of Arnold's work was so important. Okay, so just give you one slide, an idea of what is the interest here. You see, this is an old picture from a lab, from a laboratory in France, where you see this is a solid boundary and there is a flow of water. And what you see here is streamlines, velocity fields, if you like, the stream of water, and you see how regular it is. And this regularity, you may refer to this regularity as Euler equation. Ideal fluid flowing, but against the surface, or when the surface, solid surface boundary has maybe a change in shape, then you see there are a lot of structures. And these structures was certainly not the first time they were observed. These structures are basically vortical structures, vortices. And you see how complex it becomes the fluid. So let's say that this region is turbulent and is described by Navier-Stokes equation, include viscosity, and this is Euler equation. And you see how well you can distinguish one region from the other. And in a sense, it's a beautiful pictures for PDE people because it shows the transition from one regime to the other regime, elliptic equations, hyperbolic or parabolic equations, etc., in nature. Of course, this is just one of the many modern simulations of a turbulent fluid where vorticity is spreads everywhere. Some regions are in red, and you can say that in those red regions, a filament structure is forming. But instead of showing tubes, I wanted to show you this, just to give you the idea that vortices is actually everywhere, even when you don't see it, it's just because it's below a certain threshold. Now, I have a first movie here, because we have to have an idea of what is vorticity. So because I'm visiting often China, this is taken from the Chinese. I put TikTok in Chinese. They don't know what it means. It has a wing sound. And, I try to convince people that TikTok is popular in the West. There's a TikTok, I don't know whether a young lady, I said, come on, you must have it. And then when we understood each other, I said, oh, yes, every day, many hours. Okay. I don't know how it works, but look, there is a vortex ring, and she plays with her hair. Cool. And you see how they get trapped in water. Vorticity is working behind the scene. So yes, he's a mathematical operator, but is real in a sense that you see. Now I have a second video, and is a bit more dramatic, and is this one from maybe the same lady. Please don't, just, I have no responsibility for this video. Don't laugh, don't laugh. The poor guy is not happy. Yeah, I'm so sorry. When he starts relaxing, he's thinking, I didn't smoke anything particular. I don't know what happened. Okay, so this is vorticity. Okay. Now another great movie. This is 1992. Is one of the most amazing things that were done. So you see here is imagine you saw a vortex ring, and now one vortex ring pushed against or shot against another one. It's an incredibly difficult experiment to do. I know myself because I tried very hard to push ETH people and Imperial College to repeat this. This was done in Australia. And why? Because not only you want to shoot two rings, you want to shoot two rings one against the other perfectly on the same axis. This is already something difficult, but then you want to color them. You want to color one blue and one red to see what happens and how the blue and the red. So this is the beginning of my story for reconnection, because of course they collide and they reconnect. Okay, so here we have it. I'm sorry that is not so well visible. One blue, one red, they collide, and you see there are a diamond of little rings formed out of this. There's a lot to be said about this situation. Let me repeat the movie. Let's see if I can. Surely, you see, they collide and then they reconnect locally in many, many places. The business is to understand how the bifurcation in the dynamical systems takes place. And then you see this oscillatory remnant of a fluid surface that gives you the idea that one ring and one other ring, etc., they may be oscillate about the axis of symmetry because it's totally symmetric. Linear momentum is zero and is transferred radially. So it's zero in this way, may be the sum of a plus and the minus, and then the plus and the minus quantities go radially. And okay, is not so clearly visible from the screen, but if you look at the film of the movie, you see that one ring is partly blue and the other is partly red. It's still an open problem in mathematical analysis of the vortex ring dynamics. Is a beautiful problem. Greatest mathematicians worked on this. The last one I met, and he passed away still young, is Jerry Marsden. Jerry Marsden has a paper with a collaborator, an Indian guy. I apologize, I can't remember the name. That is already more than 20 years ago, trying to get in mathematics this. Is so simple. A vortex ring, you know everything about the vortex ring from Kelvin and other works, and then you want to study this mechanism of reconnection and predicting the number of points that the system bifurcates. This is the issue. And according to the intensity of the vortex ring, etc., you should be able to predict if this number is 11, like in this case, or is 7, or is 3. Of course, many people did the same in simulations. I will show you one case. This is the other video that you saw already. Why not playing again? There is an airfoil in the shape of a trefoil. Trefoil goes on, and you can check that is a trefoil. Why I'm showing this? I'm showing this because at a certain point the trefoil becomes a Hopf link. There is a reconnection of strands that I'll focus on in a moment. And then after that, I don't know why it stops here. Maybe there are 2 videos and I'm playing the wrong one. Anyway, this is the situation. You have a trefoil knot, and after some times there is a reconnection somewhere to produce a Hopf link. Okay, so we have this stage, and the picture of Feynman, I show it again. Why? Because in 55, he didn't have any information on reconnections, etc., but he had a vision. And he said, not only the big thing reconnects, he reconnects in an anti-parallel fashion, which is remarkable for that time. And then when he reconnects, he splits in something else. And what is interesting is that he may produce little vortex rings. So we have what is known now as a cascade process in terms of size, but also in terms of energy, because the filament is so thin, in that case, that energy is just where there is a filament. Yes?
So in the video that you first showed with the blue and red, and did you say that the smaller things, the smaller little loops, are purely blue or purely red?
No, they are partly blue, partly red.
So what
they
does that
inherit the reconnection. We will see other cases where the reconnection takes place in an anti-parallel fashion here. And so a little bit, suppose that this is red, this is blue. So when he reconnects, you see what happens. It takes a little part from the blue and the little part joins with the red. So it's visible here.
So the red and the blue are anti-parallel.
That's right.
Yeah, okay.
They are anti-parallel because the rings are, there is an axis of symmetry.
Oh, yeah, okay.
It's like a mirror image one another. That's why they travel one against the other. Otherwise they would travel parallelly. Okay, now this is the instance from the video where one filament under here is interacting closely with the other filament of the same knot in this particular case. Then they interact, they marry each other, and then they talk a lot about marriages and the future, having kids, all that. And then finally, they depart from one another, having maybe discussed and settled the heritage, the house, mortgage, all that. Okay, so this is the end of the story. So we are here, and here more or less here. Okay, and this case is here. All right, so we can put a transparency on this event, and the transparency shows you what's going on. So you see the red and the blue, although they are part of the same filament, but just for a matter of visualization, I have this. I put a plus and minus. Here is playing a little bit a trick, because of course a true evaluation of the Rife, if you think of the Rife, should be done by a view that is kind of solid angle around the crossings. But if the things are very local, you can approximate what you see with the correct Rife. So you see there is a change in Rife, if you like, and all right, a conservation of Rife. I want to go back just to show you, we have a +1 here and the resulting +1 at the end. Oh, as I said, it's not the way to prove that Rife is conserved, but is just a little example. Okay, so we have to understand the mechanism of reconnection in some detail, so bear with me. I will be one slide of mathematics just quickly. Actually, it's a hard work, this one. It engages 100 years of mathematics because Kelvin, in one evening, one night, produced a formula for the velocity of a vortex ring, and the people wondered where these calculations came from. And so that triggered the interest to prove that Kelvin was right. And it took many years. Then people had to improve the formula of Kelvin, etc., etc. The big business is again associated with the non-linearity of Euler equation that can be restated in a sense in this form, which is a form because of our induction law much more known to people in electricity and magnetism. If you have electricity here, you have magnetic field produced here. This is vorticity, and this is the velocity associated with the vorticity. Vorticity is basically on the filament, so you can integrate this, at least the first step, instead of a volume on the vorticity, it becomes a line integral, because vorticity, if you take it uniform along the filament, you can extract this contribution as a constant. I call it the flux in my lectures. Okay, but you see here, this again is reminiscent of a solid angle interpretation, or if you like, why not, linking number interpretation. So you developed an asymptotic theory on this, and you come out with these three contributions. One is basically the azimuthal contribution around the filament. So it doesn't contribute to the motion, to the drift of the filament in the fluid. A first order contribution comes from the binormal. L is the length of the filament, rho is a measure of the thickness, R is the radius of curvature. So basically, because L over the thickness is in a sense constant, of course everything depends on time, but you may assume that it's constant. This is a constant, and so gamma is the circulation, the intensity is also a constant. So basically this is curvature times binormal. That's the essence of the motion of a vortex filament. If you think of a ring, the principal normal is towards the center of the ring, and the binormal is along the axis of symmetry of the ring. According to the tangent direction, the vorticity, the ring goes in this direction or in the opposite direction. So that's why people who are able to do smoke rings with a mouth, they can produce visible smoke rings that travels a distance. In the case of Tate was the first to produce a smoke ring. He used a very toxic chemical solution to produce a white, intensely white rings. As soon as Maxwell, they corresponded every day, knew about this, he wrote immediately, "Be careful!" exclamation mark. You can die. And this is to Tate. And the rings were produced in Tate's lecture room in Edinburgh. So that was the first time. Rings were traveling across a room like this. So you can imagine for students was a kind of a big display.
Everyone died.
Yeah, everyone died. Everyone.
Can I?
Yes.
I add something to this
Yeah,
story?
sure.
It was in 1990 or earlier. Von Jones was invited to Swansea when he received the after the Fields Medal. He was supposed to receive some from the Prince of Wales. Remember the story? Because he has ancestor family that comes from Wales. What was the name of the professor in Swansea, his friend? You mentioned him yesterday. So he invited him to give a big public lecture. So he had also invited me to give a seminar talk. So I was there. I was out of the room because people, whatever amount of people it could take, they were there. So the rest of us, we were outside and we were watching from screen. And Von Jones told this story, started with this, that I did the smoke rings, and started with a big cigar, producing smoke rings in the amphitheater. That was the start of his talk. to explain how isotope evolves.
I
in
knew the end of the
ambient
story. He
space.
told me about the end of the story. He said, "Would you like me to show you?" I said, "No." Thank you. But, yeah, I know he was. Yeah. Okay. Fire alarm didn't. Okay. All right. So you see the velocity. The induced velocity is given in this form. This is a finite term. It doesn't contain any singularity. Here you have a singularity because when the thickness goes to zero, evidently you have a singularity in the velocity. Again, this is the problem of the Clay Institute. Do we have singularities or not? Of course, we don't have singularities in physics. That means that the viscosity, when you go to very small scales, has to play a role to kill the potential emerging of the singularity in mathematics. Anyway, the velocity can be thought of as two parts. One is around the axis of the filament, and the other one is associated with the binormal. Okay, like this. Now I'm going to show you something that I do during my lectures, and is not published. And of course, I discussed with several experts in the world about this, because it's a simple way to understand why they go anti-parallel, because this is an open question. And okay, it's not exact, but it gives you the information that you need without almost no mathematics. Okay, azimuthal contribution, as I said, let's see what happens. If we take parallel vorticity, so the two tubes that are almost colliding have the same direction of vorticity, here identify by these pluses, there is a streamline, the velocity field around has this form. And if we go to two-dimensional simulations, you see what happens. The two cores interact, merge, but they wind one around the other. So it's like the animal, I can't remember the name of in the water that was trapped by the vorticity and then was sucked inside. Why inside? Here at the center. Because in the center there is low pressure. So from outside to inside. In order to understand this, another example, very easy to do for school, for kids, we are kids, is you open your water, you keep it flowing rather intensely, you take a spoon and the concave, the convex part of the spoon, concavity is on this side, you touch gently the flush of water. And you expect that is pushed out because of the water. Air outside, water there. But no, it's sucked in. It's sucked in despite the fact that the flush of water is intense. Because inside the flush of water, the pressure is lower than the exterior pressure. Okay, so this is the reason why the anti-parallel vortices go one around the other and they merge instead of separating the diagram of Feynman. Let's see how this azimuthal contribution works in the case of anti-parallel situation. Now, pay attention. Here we have a point of symmetry in the plane, in this case, where I call it P, and this point is the point, you see the streamlines are so intense and they are going in the same direction. That means the pressure is very low at the point. So we have a low pressure here, and let's say the minimum pressure here, the minimum pressure there. Okay, so 3 points where we have, is like the three-body problem of Lagrange and celestial mechanics. 3 points where.
But why should we have low pressure at point P?
Why?
Yeah.
Because there is a theorem, or there is a result due to Bernoulli, very old. I'm going to show you now, where the amount, let's say, of velocity and the pressure should be constant. If velocity is very high, pressure has to be very low. I'm going to show you, and velocity is very high from these diagrams, let's say. All right, so remember we have two contributions from this side and this side in terms of theta. Then we have the binormal contribution. Here's one and here is the other. And the antiparallel configuration, you may recall the Bernoulli theorem. Bernoulli says the pressure at P is summed by the contribution. This is basically kinetic energy density, the velocity at P squared, and this is a constant. If P is at the minimum, the velocity has to be at the maximum. In this case, the velocity is at the maximum, so P is at the minimum. And you do a little bit of local geometry, something very simple. I don't have time to speak about this, but it's just really drawing a piece of geometry, nothing else. You put P at the center, and then remember, we have E theta and D theta in the here, but we have also the contribution from the binormal locally. Binormal from one strand, the binormal from the other strand. But note that the binormal, because of the curvature of the filaments, are towards the point, are towards the point. So what happens is they cancel each other. Binormal contribution cancel each other, and then we have to take into account of this alpha to do our little algebra, so to speak. If we compute UP, the velocity at the velocity at the center squared is given because of the cancellation of the binormal component. We have the contribution from the azimuthal terms, and the azimuthal components give rise to this 1 plus cos alpha. You want to maximize the velocity, so alpha has to be 0 in order to have maximum velocity and minimum of pressure. And that's it. That's it. This is just the way to show, let's say, that antiparallel configuration is the dominant mechanism here. Of course, I want to go back because I showed this to a number of experts, and the experts in fluid mechanics, they raised instantly the question, oh, but you don't have any viscosity here, and the vortices are so close to one another. Yes, indeed, I don't have any viscosity. I'm well aware of that. You can put viscosity and you increase a complication in the mathematics, but not in the concepts. The concepts are there. All right. Consider then antiparallel reconnection of a polygonal curve. So you go from smooth curves to polygonal curves, and you can work out in a few steps some mathematics. If you assume antiparallel reconnection locally, then you are in this situation, and then in a piecewise linear context, you think, okay, they approach each other and they cancel each other as it happens in reality. If they cancel each other, you can show in mathematics, but also visually, that the apparent rise -1 stays the same, is conserved. So you go back to mathematics and you want to prove this rigorously. We did it in a piecewise linear manner, in a piecewise linear context. Okay, so the theorem goes like this. Work was done with Dewitt-Sumners, and Joe Lang now works in biophysics, I think is in San Diego. The rise of two disjoint-oriented polygonal curves A and B is conserved under antiparallel reconnection of A and B. And so this is an important thing because you think of helicity. Helicity, even for one structure, is expressed in terms of self-linkage, and self-linking is given by Wright plus twist. If Wright locally is conserved, a cross reconnection is conserved, and you have a change in helicity for some reason, for example, dissipation, etc., then the change in helicity has to be ascribed to twist only. And this was a little dispute I had with Keith one time when we were in Moscow, because he wanted to prove that twist is conserved. And at a certain point, everything dropped, because the following week, William Irvine showed in a paper in Nature that Wright is conserved and twist is transferred. I wanted to convince Keith that the twist had to change because it involves high derivatives. But he said, well, you have to prove it. I was off. So we went this way to prove it. Instead of working on twist, it was much easier to work on Wright. We published this paper at the same time when William Irvine published his own result. And funny thing, different worlds. I feel to belong to mathematics, and he's certainly in physics. And he asked us to allow him to state that the result he found was independent from ours. Okay, sure. It's independent. It's done in the lab and with measurements and ours. No point to be so picky in pretending that. But it went well. And corollary two, since under anti-parallel reconnection of A and B, total torsion is also concerned. Any change in helicity is only due to a change in intrinsic twist. And this is, for physical reasons, is very important, because that means that a lot of energy transfer is due to the exchange of twist rather than anything else. And so because we care about the energy transfer in mechanisms, then we have to understand how to measure or evaluate intrinsic twist. Very, very hard to do it. Okay, this is a numerical simulation done by the group of Fazil Hussein and Jim Zhao, and he's back to Beijing, Beijing Institute of Technology. He is very, very good. This guy, we hope to collaborate in the future. But in simulation, you can measure the exchange of twist, because in simulation, if the CPU allows you to do this, you can go down to the scale of filaments of the bundles that form your tube. All right, here we have a beautiful, beautiful movie from a Russian group. It didn't receive the cover that William Irvine had with Western journals. I publicized this as much as I could because I believe it's exceptional. Anyway, here we go. You have, let's say, a helical, almost helical filament in water. And as this helical filament is kind of pushed to get closer and closer one strand with another, the two helical strands become very close at the point that they interact by Biot-Savart, and they merge and they reconnect and they separate. And the beauty of this is an extremely difficult experiment. You have to position the camera exactly at the point and time where reconnection takes place with the right light in order to see physically in terms of water what's going on. And okay, they deform each other, they get close and close and close, and then they reconnect and they leave each other. Let me see. Okay, you see they deform, they get almost planar. You see the swirling of the water, the bubbles, and then look, they merge and they separate. Yeah. By the way, if we go back a minute, let's see if okay. You see that the reconnection leaves behind, in reality, a little strand of vorticity, like the opposite of a bridge. Okay, you see here, some vorticities disperse.
It had to use anti-parallel to bring
They
to
go
a
anti-parallel. No, they go themselves anti-parallel.
Yeah, I see.
It's natural. It's nature that does this. Okay. All right. So you see, this is the situation at the beginning. One filament that goes like this. I put the blue and the red just to mark the crossing. And then from the pictures, they go anti-parallel naturally, forming this loop. And it detaches with, I put here some yellow tracer over the picture just to show you that there is still some vorticity left out. And then when they separate, there is still this little vorticity that is killed by diffusion. This is a numerical simulation by the same group, Hussein in Houston, and you see the same stuff. Remember, they now have a bundle of field lines inside, so it's very visible what's going on. And there is this bridge they can get from direct numerical simulations of Navier-Stokes equation. You see, this is already 15 years old, and there are many other papers on this, especially the Chinese group. There is now Yu Yang in Peking University that is doing a fantastic job on this. This is the only video we have. We change the scale and we go to 1 millionth of a meter. So we go down 1,000th time of a millimeter scale. You use as a tracer. Imagine that if you are in water, you trace vorticity with bubbles, very tiny vapor bubble, for example. In that case, you produce solid particles of hydrogen, okay, solid hydrogen particle, and you let it go in the bath of superfluid helium-4. This is a Lathrop laboratory in Maryland. It's a fantastic place where he showed for the first time, 2019, the reconnection of two vortices, quantum vortices in helium-4. It's very rapid. So this is the way it is. And at a certain point, you will see the two, you see the snapshot of almost a snapshot of the two vortices. Let me play it again. I should have prepared this in a slow motion. Here, they will appear, they interact, and they leave each other. So the mechanism is similar. So what we did with Simone Zucker, this is a famous paper that Simone wrote with Carlo Berenghi in Newcastle. Here we are, thanks to Alice that mentioned the GPE, we are in the context of Gross-Pitayevsky condensates, so bosons, photons, etc. And so the code is the Gross-Pitayevsky code, where you see a vortex ring interacting with a vortex straight line. As Alicia said, this is a visualization of a ring. In actual fact, the ring has a nodal line for the wave function. So we actually see what happens to the nodal line, to the zero amplitude wave functions. And then we visualize the ring or the straight line by assuming or by identifying the points in space where density is not zero, is different from zero. So you have, the covering of a ring or as a torus. Okay, there is a reconnection, and then they go. And then eventually they open up, etc. So this is one of the first instances where reconnection in quantum system was shown by simulations. I had the luck to know Simone when I moved to Italy. Simone lives in Verona, and he's a great, great man for fun. He does research, and for living he teaches at high school, but he has a PhD, traveled the world, and they were tired to travel as a couple in one place, and the other said, hey, let's drop everything. Let's find a position. And then if I have time, I do research. So he does research. He has a number of publications. The University of Verona gave him an office because he's so talented and good. But the position probably is better to keep it in high school. Less stress in administrative things and all that. Anyway, here is my proposal. What about repeating the head-on collision of vortex rings in quantum systems? So he has a code, he did it himself, etc. So here we have the vortex rings already close to one another. So you see already the perturbation. If you start everything from far away, the two rings are perfectly circular. And what happens is this. They approach. I'm sorry, these are slow motion, very slow motion. So maybe I should improve. By the way, we have also the planar projection of what's going on, because it can be done some analysis on that. And as they approach, hopefully tomorrow or we'll see what happens.
Oh, I see. So we are seeing a movie now.
Yeah, we see.
I see the time. Yeah, I see the time.
Yeah, the time is moving.
Yeah.
Time is moving. Yes.
I don't know if all the movies are like this. That's terrible, because I have several, but I don't know how to control this. Okay, let it.
But keep talking, and we will keep watching.
Wait, there's a question.
Oh God.
No, not.
Just leave it and we'll have some questions.
Oh, it doesn't do anything. Okay, what about this? Oh, also.
It
this-
does.
Yeah, it moves.
Changes it. Yeah, the time changes faster here.
I'm afraid to,
Yeah, now it moves. Look, yeah.
okay.
And can I ask a really like
Yeah,
tricky-
sure, we have time.
maybe this is a very stupid question, right? But when I go and imagine these tubes with the sort of central curve is the zero density or the zero frequency curve, where do the waves come in, and does the wavelength affect the density? Like how do I imagine the wavelength going through this zero axis, or should I imagine it slightly differently?
First of all, these evolutions are full of information that you do not see. One information is sound. As they move, they emit sound waves, and the sound waves contribute to the, let's say, oscillation that you physically see in the density profile.
Okay.
Then there are other mechanisms, mechanical waves that are produced by instability, natural instability, Kelvin waves. So these waves are due to the tiny perturbation on the nodal line. And if the symmetry is preserved at all times perfectly, then they do not evolve. If there is a break in symmetry, mind you, there might be a break in symmetry due to numerical noise as well. And so immediately they start to develop. So there is a sound emitted that you do not see that interact with the rest of the system, plus instabilities that may be triggered even if you don't have, if you have the care not to change the symmetry of the system, that they develop from numerical reasons. Okay, so you saw the interaction of a Hopf link producing smaller structures, basically. I don't want to run this again, but I'm afraid I do with this. And here we have two loops, and they interact, they reconnect. We start with two loops that are unknotted and unlinked, and then they interact at a certain point, reconnecting and forming a Hopf link. So you can show that not only you can go in one direction by increasing topology, like in this case, but you can go also in the opposite direction. You start with a topological complex system and you go to unknotted, unlinked loops. Here you have the formation of a Hopf link, and then a further reconnection, change colors, you go back to two filaments that are totally unknotted, unlinked. And so there are a number of examples. This is the production of a trefoil knot. Instead of starting from the trefoil knot, we can produce a trefoil knot a la Kelvin. So it's similar to what William Irvine and Kleckner have done, but reversing, in a sense, the situation, i.e., just being consistent with what Kelvin wanted to see. I don't know why he stopped. Okay. So again, this was in mind of Kelvin, producing two vortex rings that when were closed, they were interacting and producing a knot. And that was a way to figure out, to envisage the natural production of new chemical elements in nature. You see here is a trefoil knot, produce one color only. Then they interact further, you have a Hopf link, you reverse the topological cascade. Okay, let me skip to the next because, okay, this is another one.
Renzo?
Yeah,
Since it usually goes from the knotted to the unknotted,
Yes.
to go the other way, you exactly set like the last situation to be the first, and
no, although GPE is reversible, you don't do that way. This is a great, it would be a half an hour lecture to students. Why students, I mean undergraduates, you have to, in order to produce the knot, you have to figure out, i.e. trial and error, the exact initial condition.
Yeah, that's.
So
the
this
tricky
is
part.
governed by a differential equation, is showing very clearly how initial conditions, very, very precise initial condition, trigger one evolutionary path rather than the other. Because the students don't have this sense of initial conditions.
Yeah.
And you give usually the same example, t equal to 0, t equal to 1.
Yeah, that was the question. How do you find the perfect initial
No.
condition? It's just guessing.
It's
Right.
just guessing, you know some things about the dynamics, the binormal curvature. So the two curvatures at the point of interaction,
them to
they
be-
have to be the same with a difference in binormal so that they hit each other. For example, if you take elliptical loops as we did, planar loops, and you try once and another, trial and errors many times, you will discover as RF found that if you take an ellipticity of one elliptic ring and incline and the angle, the mutual angle of inclination of a particular value, then you have with the two planar loops moving one along in the same direction of the other, but the one behind catching up because the other is larger, so it moves the smaller moves faster. It catches up at 2 points rather than 4, and then it produces a half link.
Okay.
So that was done already. Yes.
Just a comment on this.
Yeah.
Well, two things. First of all, you showed that basically you start with the perfect geometrical initial condition to reproduce the trefoil from the collision of two rings, right? But then after the trefoil is produced, then you observe that the structure reconnect again and forms again the two loops.
Yeah.
Every time.
Every time.
Okay, because when I first met Koya Shimokawa in a
Yes.
conference,
Yes.
he showed me the picture of DNA recombination and how
Yes.
you can create the cascade of the
Yes.
topology of DNA. And I asked the question to him because I only saw the higher topology to lower.
Yes.
So I asked him if he could go backward, and he said yes.
Yes.
About this is sort of like in DNA you can highly control
Yes.
the recombination, the reconnection.
Of course.
So
yes.
you go through stage of equilibrium configuration time by time.
Yes.
Which means that you can control all the initial condition every time.
Sure.
Whereas you cannot do this.
No.
So that's the reason why they reconnect again back to the two loops.
So I'll mention an amazing work that Carlo Barenghi did recently, and what he observes and what people know is happening is that it depends on which scale you have in mind. If you have the scale of the whole phenomenon, then it always decay to loops. So that's turbulence. Structures interacting in a complicated way, simplifying gradually through reconnection till all loops are formed and then they dissipate or disintegrate. But if you follow locally in time, step by step, like having screenshots instead of a movie, you can you observe that on time to time, there is a transition towards a higher topology. This does not survive. So you can go from a trefoil knot to a 4-crossing, 5-crossing, 6-crossing knot, but then the 6-crossing knot still decays down. So you have transitions where I call the reverse cascade, and the reverse cascade is also known in turbulence. So it may happen. So if you think of the whole phenomena as everybody think of, then there is a natural decay in terms of structures, in terms of energy. But if you think locally as a sequence of pictures, yes, you can have an increase of topology. Yeah. So the dominance is a topological cascade. The local aspects are reverse or cyclic, what I call the cyclic topological cycle. Topological cycle is 2 loops, they interact, they form a Hopf link, they separate, and they may still form another Hopf loop, but at the end, as they decrease in length, because all the time there is a reconnection, you have to think that physically you eat up a little bit of length of energy. And so at the end, you end up with little loops, so to speak. Little is Okay, let me skip this. It's so slow. All these movies are will be available. Maybe I just make them. I speed up them.
So for these reconnections, you need the initial conditions that will bring anti-parallel close by.
No,
Who said about initial conditions?
I said initial conditions in order to, how to say, expect to go from unknotted, unlinked loops to trefoil. This reverse cascade, reverse topological cascade, going up in complexity is not natural, but you can make it natural by engineering initial conditions. So suppose you run 100 times.
I thought this was a local phenomenon.
It's a local
very
phenomenon.
local
They go
phenomenon.
anti-parallel themselves. But of course, you can
Yes.
engineer initial conditions.
So the resulting topology could be more complicated, could be simpler. We don't know
Absolutely.
because it is a local phenomenon, right? So my
Absolutely.
question was, there are no external agents to, it is only a question of internal energy and the local conformation. Is that so?
It is
Like
correct.
in DNA recombination, we have external agents, the topoisomerases.
Okay.
You see what I mean?
Yeah, I don't like to have this
But it
type
is.
of wording.
But it is.
No, the external agent acts globally on the fluid. I'm not doing anything. Vortices are going anti-parallel because of their the distribution of pressure in the fluid.
Mm.
They go naturally, locally anti-parallel.
I see. I see.
If I want to produce a particular topology, if I want to do this, not nature, then better to start with an initial condition
You can engineer.
where they are already anti-parallel.
Yeah.
So I get quicker. I start with anti-parallel with a configuration that shows local anti-parallel arrangements, but then the evolution is free. I just set up the initial conditions so that I invite the loops to reconnect and produce something more complicated. If I let it go, it gets more complicated, as some was saying, it gets more complicated, but naturally they reconnect in an anti-parallel way, and then they decay to unknotted, unlinked loops. So it's different from DNA. DNA, they locally enrich the solution with enzymes, and the enzyme produces reconnection. Here is total natural. Is Biot-Savart, is field theory talking. Differently is the question of Alice when she said, if you want to produce a trefoil knot, how to do it? You have to engineer the initial conditions. You have 100, infinitely many, but let's say you have 100 choices, but only one of these 100 gives you the trefoil knot. So is the role of initial condition, how sensitive is the dynamical system to initial condition? If you pick those initial conditions, then you get a particularly increased evolution towards evolution towards an increased topology.
Yeah.
Is there
But
any
everything
way
is not-
to find that there's some energy, particular energy in that initial condition that brings you up in the cascade?
Well, sure, it's very easy. Think of LIA, curvature times binormal. Energy is basically curvature squared. So if you localize energy in terms of curvature, you have high energy there.
But you know that that one has a different energy than, okay, they all have different energies.
A straight line, you may say, of course it has energy, but you may say it has no energy.
Okay.
Curvature is zero, it's just swirling around the axis, doesn't move at all. Yeah. Okay, sorry. So this is also a slow simulation, but we went for surfaces. So you have your Hopf link, and what you see is a Zeifer surface. Actually, it's a particular Zeifer surface. We have infinitely many Zeifer surfaces. This one is the Zeifer, is the minimum area Zeifer surface. So it's a particular surface in terms of physical contents. And as I run the slow simulation, you see the simulation, the evolution of a hot link, as we saw it before. It reconnects, it produces smaller loops, and also the surface goes the same. Because Rife is conserved during reconnection, maybe one reconnection will take place either here or here, I can't remember, then the surface orientability is preserved. And being preserved, it carries on information on the physics, and you can prove in simulations that all the reconnection process is governed by a sequence of continuously decreasing minimal surface energy. So this is a very interesting detector for evolution in quantum system, and it has some bearings also in string theory. Anyway, this is what's going on. There is a reconnection probably taking place there. I can't remember where is one of the two sites. And you will see in a moment that the surface breaks, or here.
Yeah.
It breaks there. And so you're still going down in minimal area.
And there is another happening
And
there.
then the other one. And then a third one will happen here with the production of two smaller loops. Now, of course, if you allow the simulation to go on, this also keeps going, reconnect and gets smaller and smaller loops at all times. So this is also, I find it beautiful. Okay, so you see, yes?
So going back to Alicia's question,
Yes.
if you wanted to make a higher topological structure, you need to go through a number of crossing changes. If each crossing change dissipates the energy of the system, then you do have to start in a higher energy configuration to get to a more complicated topology.
So the question?
Is that what you were saying?
Yeah, I was asking if that specific initial condition of the 100 of initial conditions, it needs to have more energy, some specific energy to go up in this case.
That is correct.
So do you know, is it very dependent on how the reconnection happened, or is there like a kind of quanta of energy released in a reconnection?
Again, there are several energy contributions. Let me repeat, there is also a sound contribution that you don't see any here. It's everything, the background is white, but if you consider sound, you would see a background full of different colors in terms of sound energy. Quantum energy, of course, also present.
Okay.
Sure, you have four contributions at least. The standard classical kinetic energy, the quantum energy, so to speak, and the sound is associated with both. Mechanical waves are associated with kinetic energy, and there is a potential energy as well.
So it's you can't say there's a fixed amount per connection. It's just, it's too complicated.
No, through reconnection, you decrease energy, for sure.
Okay.
Because it gets dissipated. In this case, as a quantum case, I cannot say dissipated in viscosity. There is no viscosity, but it goes in sound. Sound is produced. I mean sound. Yeah. Sound. Okay. Surfaces, minimal surfaces bring us to the beloved field of minimal surfaces for mathematician. Euler was very interested. We are back of almost 300 years. Lagrange was very interested, and this is an interesting surface. There are two rings. Now these rings are made by metal, okay? Solid rings, one is here, one the other. When you see these things, these are like controllers. There are physical sticks with which you can move the rings, the solid rings in the soap film. You remove the soap film, you put the laser that gives you this green color, and that is the famous surface studied by Euler, Lagrange, and many others. I was very lucky because this was done one of the big strengths in the mathematics department, in the world top mathematics department. They do have an experimental section devoted not to physics, but to mathematics. And I was very lucky. This is in Cambridge. And the now chair in mathematical physics in Cambridge was a friend of mine at the time of Princeton at the Institute of Advanced Study. His name is Ray Goldstein. And so when I knew that he was doing these things, I was extremely happy. I went there and he showed me these pictures. You see, here we have a transition in topology just by making these two rings departing one another. So remember, these are physical sticks with which you move the two rings. You need maybe some computer that does this for you, and a camera, high-speed camera, and all this. And you go through a singularity, a fluid type of singularity. Very beautiful. When I saw this, I said, but I know an experiment. We have to do an experiment on something old that has never been done. And who proposed the experiment? Well, the experimenter is here. I challenge you to tell me the name of this guy. You know, he's a famous experimenter. You see, he's playing with soap films and the trefoil knot. He's an experimenter that is not working in fluid mechanics. He is Courant himself. And this lady is an assistant. I'm sorry, I don't know the name. And he wrote a one-sided soap film in the form of a Möbius strip. Is easily formed, yes, it is true, and it can jump to a two-sided film if the wire boundary is suitably distorted. So I checked if he done that, but no. He wrote a paper for students, for undergraduate students, and it's a beautiful reading where he describes in his own drawing what he had in mind here. You start with a soap film in the Möbius band form, and then you distort it. Imagine that you open up this coiled wire. The boundary is a wire. These are the sticks that control the wire shape. And here I have problems to understand what he has to say, but I know what he has to say. I will show you. This is the paper. It's a beautiful paper for young mathematicians. Soap film experiments with minimal surfaces. You know, he played an important role in the Fields Medal allocation to, Fields Medal was given to Douglas, 1933, after a parent, I don't know, relative, a grandparent of Alice Rado, and great mathematician. So yeah, he was, of course, calculus of variation and inspiring generations of people. Trouble with the Douglas. Douglas, influenced by Courant, said in the Fields Medal paper, you go through the assumptions. And the last assumption is crucial. It says, I won't care about different topologies. That's all. It's a simple word. Is written in a more sophisticated way. But basically, that stopped people to look for the relaxation, minimum energy, minimum surface or plateau surfaces of knots and links. So don't follow the flow too much. Douglas, yes. The others, they all followed. And so they never consider more complex topological cases to study up to now. I was in Normale in Pisa, and there are several people doing calculus of variation, great tradition, and they said, did you consider this? Why not? Well, I don't know. I never thought about. I said, I know why, because Douglas wrote, I'm not considering this. Everybody went in that direction. Sorry, it's online now. And okay, here we have the unfolding process of the curve that probably Courant had in mind. And so you start with a simple curve, no knots, simple curve that is making a coil in space and evolves and evolves and evolves and so on and so forth until it gets a planar circle. And this curve is so easily realized with sine and cosines. And so this is what I did with Francesca. And you see cos and sines, S arc length, and t is some fictitious time. When I had this equation in 2006, and I met visiting Cambridge Ray and doing soap experiments, I said, okay, this can be done immediately because we set this equation on a computer. The computer does this transformation on a material filament, on a metal filament. If you do rule surface geometry, as you taught as undergraduate, you include a second parameter, i.e. some thickness of the line, so that makes a ribbon. Then you have a Mobius strip initially, and then you keep going like this. And then is a ruled surface, okay? So it's not the actual physical surface because it's a fluid surface. It would adapt, but as much as you can go, you go with mathematical. You see, here something happens. The hole disappears. And you can predict the disappearance of the hole at 2/3 with something strange that mathematics cannot handle. Evidently, there is some singular aspects of your equations. And the singularity, again, is smoothed out by the fluid viscosity. And so you won't see any singularity till you get a flat disk. Now, here is a beautiful example of a change of topology, not on the boundary. The boundary line is an unknotted loop, but on the surface orientability. Mobius band is two-sided, disk is one-sided. And when I explain this to people, Keith and Ray and Adriana Pesci, his wife, the wife of Ray Goldstein, we were puzzled. What happens? And Keith is a great master in asymptotics on microhydrodynamics. So I was in good shape. I said, well, you do the mathematics on this because I don't know what's going on. And everybody was intrigued. And so we did. And okay, this is the Mobius strip. You have a second parameter here in space, mu. And when mu goes to a certain value, 1, then you get just let's say, the loop. All right, so we are ready. We go for the Poisson-Laplace-Young equation for plateau, and this is the situation, is a surface in soap film, in air, so pressure on both sides are, say, 0 or the same value. So what matters is the mean curvature given by the sum of the principal curvatures of the surface. And this is the experimental setup. You see here there is a hole, and it's very hard to see what's going on. But imagine what you see here, the sticks are the ones that control the physical form of the wire, and the red stuff is the soap film, and then you deform the thing in order to go from, let me go back one slide. You start with this configuration, and then you deform in the two edges of the ribbon in order to get the disk. But while you deform this, at a certain point, the hole disappears, and there is a restructuring of the surface in here to get to the oriented surface. So, all right, here we are. We have the setup. At a certain point, the hole decreases, decreases, decreases. We are in 3D, remember. So we see things from top, but we are in 3D. At a certain point, it disappears. And I show you, this is the plateau borderline, is where the green soap film ends against the wire and before the collapse. And this is after the collapse, with the formation of this strange twisted fold singularity. Frames are from high-speed movies, so he applied, he got, these things involve immediately a lot of money, 100,000 euros, because you want high-speed camera, lasers, computing, following the computer evolution, etc., etc. So this is his movie from Ray Goldstein. Okay, so a soap film Mobius strip changes topology with a twist. The Mobius strip soap film, first of all, is the green stuff. You see, these are the sticks to control. And after the topology transition, look, it goes, the hole goes away. You have tiny bubbles here and there. And now you see in motion what's going on. They depart, at a certain point, we have this beautiful caustic in optics. And this is the wire, and this is the soap film boundary that makes this thing. All right, so this is before, this is the transition. Before, you have a linking number between the plateau border in green and the wire, and then you have a jump in linking number when you get to the disk oriented disk configuration. The jump in topology is a measure of the fact that you change orientability of the surface, and not surprisingly, you get something that is resembling very much the formation of the twisted magnetic field. Indeed, locally, I was very lucky because locally you have an inflection point. So you can apply the analysis that I showed you before. Near the inflection point, you can do still some mathematics, and you discover that you are uncovering the production of a twisted saddle geometry a la Zeeman. So that's why this is the rider master twist move in 2D. And so this is the end of my story. You can do a ruled surface analysis as much as you can, but you can also apply Bracke's surface evolver to follow more realistically the evolution of this Möbius band. There is a difference in energy because ruled surface geometry can get just a little bit of the surface, and the twisted fold catastrophe visibly in front of you is there. So these are the simulations. And with this, I thank you very much.